In part 2 of this section, we're going to switch gears a little bit and now think about what does the second derivative, or f double prime, tell us about the graph of a function. And so on the screen, I have two different functions that are increasing. So both of these functions have first derivatives that are positive. These are increasing functions. However, if we look at these graphs, we know that they are very different graphs. They're giving us a different story about that increase. And how are they different? Well, the graph on the left has slopes that are getting bigger. It's increasing at an increasing rate. That's kind of like exponential growth when things are growing at a faster and faster rate. Whereas the graph on the right, it's flattening out. The slopes are actually getting smaller. It's increasing, but we could say it's increasing at a decreasing rate. All right, and so what does that mean? If the slopes are getting bigger, that means the first derivative is increasing. Or in other words, the important thing I have written down is when the graph is shaped like I have shown on the left, the second derivative is positive. So this is the picture of a graph with a second derivative that is positive. We say that this graph is concave up. So anytime the slopes are increasing, we say the graph is concave up. It has that upward curvature. Whereas the graph on the right, the slopes are decreasing. And anytime the slopes are decreasing, we say the second derivative is negative, and we'll call the shape of this concave down. It's curved down. Okay, so the second derivative tells us whether a graph is concave up or concave down. So it tells us basically which way is the graph curved. So let's do an example. Let's determine where the function e to the negative x squared over 2 is concave up, and where is it concave down? So this problem is asking us, where is the second derivative positive, and where is the second derivative negative? We can solve this problem almost the same way that we solved those increasing-decreasing problems from part 1, with one big difference. We'll be analyzing the second derivative. Okay, so let me show you what I mean by that by just doing this example. So we're going to have to compute our second derivative. In order to do that, we have to find the first derivative. And so I have the first derivative written on the screen. I use the chain rule to do this. We have e to a power, and so my outside derivative, I just copied that down. E to the negative x squared over 2. My derivative is e to the negative x squared over 2. And then here's the chain rule part. We have to multiply by the derivative of the inside. And with these exponentials, the inside is always the exponent. And so the derivative of the exponent is right here, negative 2x over 2. And then I just canceled those 2's out, put the x in front. And so that's how I got my first derivative is negative x e to the negative x squared over 2. All right, so there's my first derivative. Now I have to find the second derivative. And so we should ask ourselves product rule, quotient, chain rule. So what do you guys think about that? Product rule, quotient rule, chain rule. We are going to use a combination of the product rule and the chain rule. So I have my work for the product rule written in purple. So f was this negative x. G is the e to the negative x squared over 2. That means my f prime is negative 1. G prime, technically we already computed this, but I'll do it again. We use the chain rule here, so we have e to a power. I just copied that down. Then I have to multiply by the derivative of the inside. The inside is the exponent, so I have to multiply by this negative 2x over 2, and then I would cancel those 2's out. And so now my second derivative is going to be f prime times g plus, I think did I lose my plus sign in there? I mean, I guess it doesn't matter because I put that minus there, but I'll put the plus in. Plus, there's my g prime times f, plus g prime times f. And so I guess in the end, it is going to be a positive because we have a negative times a negative in that second term. So let's see, yep, I got negative e to the negative x squared over 2, and then plus, and then I just multiplied these two x's together. X times x gave me the x squared, e to the negative x squared over 2. Okay, so there's my second derivative. All right, well, what are we trying to do? We're trying to figure out where is this function concave up and where is it concave down. So we're trying to figure out where is this second derivative positive and where is it negative. And so the process we're going to go through is going to be very similar to what we did with those increasing and decreasing functions. We're going to take our second derivative, we're going to set it to 0, find those critical points, then we're going to make a number line, and we're going to analyze the sign of the second derivative. All right, so I set my second derivative equal to 0, and then I'm going to solve this thing by factoring. And so if you take a look at the second derivative, both of the terms have an e to the negative x squared over 2 in them. Okay, both have that same exponential expression. So that's my GCF. I pulled that out front. And then in the first term, we're just left with the negative 1. And in the second term, we're left with the plus x squared. All right, so that's how I got this next line. I pulled the e to the x squared over 2 out front. I'm left with a negative 1 plus x squared. That's the same thing as x squared minus 1, and so I factored that as my difference of perfect squares, x plus 1, x minus 1. Now that this expression is factored, we can set each of the factors equal to 0 to solve. E to a power is never going to equal 0. If you wanted to solve that kind of equation, you would have to take log of both sides, but you can't take log of 0. So if you want, you can just remember when you have e to a power, never equals 0. So that doesn't give us any solutions. The only solutions we have are from the other factors, x equal negative 1 and x equal positive 1. So now that we found our zeros of the second derivative, we are going to create that number line. We're going to put the negative 1 and 1 into our number line, and then pick test values in each interval. So I chose negative 2 is smaller than negative 1. 0 is between negative 1 and positive 1. And 2 is bigger than positive 1. I took the test values and now I'm plugging them into my derivative, or sorry, my second derivative. And so you could plug them into this right here. Here's your second derivative. It looks like when I put this into my calculator, I plugged it into the factored form. Doesn't really matter. So I took, for example, negative 2, and when I plugged it into my second derivative and put that into my calculator, I got approximately 0.4, but the information I care about is it's a positive number. And so I put a plus sign into my table. And then I'm going to do the same thing with the 0 and the 2. And I didn't write out my work for 0 and 2, but I did the same thing. I put it into my second derivative. I used my calculator, and I recorded the fact that I got a negative when I plugged in 0, and I got a positive when I plugged in 2. And because we're analyzing the second derivative, the positives tell me that the graph is concave up, or has this upward curvature. The negatives tell me the graph is concave down, or has a downward curvature. And so to answer the question, where is it concave up? That's where I have the plus signs. So negative infinity to negative 1, 1 to infinity. And where is it concave down? That would be where I have those minus signs, so negative 1 to 1. All right, let's do another example. This example is similar, except we've got one extra question here. So the problem says, determine where f of x equals x minus 2 to the third, x minus 1 is concave up. Where is it concave down? So that's asking me where is the second derivative positive, where is the second derivative negative, and now they want us to find all inflection points. And inflection points are going to be places where the second derivative changes sign. So places where it changes from positive to negative or negative to positive. So to answer this question, we're going to do the exact same process we used in the previous example, except we're just going to have kind of one extra thing we're going to have to write in our answer. So we have to find the second derivative, and I guess to do that, we have to find our first derivative. So product rule, quotient rule, chain rule. Looks like product rule to me, and chain rule, I guess. So f is going to be the x minus 2 to the third. G is x minus 1. For f prime, this is where technically we're using the chain rule, so I brought the 3 down, 3x minus 2 squared. And then I have to multiply by the derivative of the inside. The inside, though, is just this x minus 2. Derivative of that is 1. And then g is x minus 1, so g prime is 1. All right, so we did f prime times g plus g prime times f. So there's my first derivative. And now I'm going to have to find my second derivative. And I think I might do a little bit of algebra to this first derivative just to make finding that second derivative a little bit easier. And so the algebra I've done is I've decided to factor. So this is still my first derivative. I notice that both terms have an x minus 2 in them. The first term has an x minus 2 squared, and the second term is an x minus 2 to the third. So I was able to take x minus 2 squared, that's my GCF, and pull that out front. When I pull the x minus 2 squared out front in the first term, we're left with the 3 and the x minus 1. And so that's what I have written down here, 3x minus 1. If I take x minus 2 squared out of the second term, well, there's 3 of them, so I have 1 left over. Now, inside the parentheses, I'm going to distribute and combine like terms. So I distributed the 3, that gave me the 3x minus 3. And then combine like terms, now I get 4x minus 5. All right, so I did some factoring. It's just kind of a good skill to know how to do. And this is going to enable me to just use the product rule to find this derivative. So I think we're ready to find our second derivative. We're going to use the product rule again. This time the f is x minus 2 squared. The g is 4x minus 5. So f prime, technically I'm using the chain rule. I brought the 2 down. 2x minus 2 times the derivative of the inside, which is just 1. Derivative of 4x minus 5 is just 4. All right, so f prime times g plus g prime times f. And now that I have my second derivative, I'm going to set this equal to 0 and solve. Once again, I'm going to try to use that same kind of factoring trick that I used earlier. So what I mean by that is I notice both of these terms have x minus 2's in them. So I can factor that out. We could also pull, this one has a 2 and this one has a 4. So we've got a GCF of 2x minus 2, and that's exactly what I've done in this next step. So I took the 2x minus 2 out front, and so then the first term we're just left with that 4x minus 5. Second term, if you take a 2 out of the 4, you get a 2 left over. And I took one of the x minus 2's out, so I've got 1 left over. So now I'm going to distribute and combine like terms inside those parentheses. So I basically just distributed the 2. So right here I distributed the 2 to the x minus 2. That gave me 2x minus 4. Combine like terms, 6x minus 9. So now that my second derivative is in factored form, I can just set this thing equal to 0 and find the solutions. All right, so here's my work. I just made it a little bit smaller so we can fit more stuff on the screen. So I took my second derivative, I set those factors equal to 0, I got x equal 2, and then add the 9, divide by 6, so 9 divided by 6, which is 3 divided by 2. All right, so these are two places where the second derivative equals 0. And so the whole reason we did this is because we're going to use those numbers to create our number line. So I have drawn a number line. I put in 2 and 1.5, or 2 and 3/2. So these are the zeros of my second derivative. I'm going to pick test values in each region. So I chose 0 is smaller than 3/2. 1.7 is between 3/2 and 2, and 3 is bigger than 2. I'm going to take my test values and I'm going to plug them into my second derivative. I chose to plug them into the factored form down here that I've just circled, but really you could plug it into any of these purple lines I have. But I took 0, I plugged that into my second derivative. I got 2 times -2 times -9. That gave me positive 36. But the important thing about that number is it's a positive, and so that's what I had to put into my table. I'm going to do the same thing for 1.7 and 3. When I plugged 1.7 in, I got a negative. When I plugged 3 in, I got a positive. The positives tell me the graph is concave up, upward curvature. The negative tells me it's concave down. And so I've written down in blue my answer to the first two questions. Where is it concave up? That would be -infinity to 3/2, 2 to infinity. Where is it concave down? That's going to be 3/2 to 2. So finally, the last question they asked is where are the inflection points? Inflection points are places where it changes concavity. And so those numbers you put into your table, the 3/2 and the 2, are both inflection points because the second derivative changes sign at those locations. So inflection points are going to occur at 3/2 and 2. And when we write down our inflection points, I do want you to give the answer as an ordered pair. So the 3/2 and the 2 are the x values. Those are x values at your inflection points. You're going to give me the y values as well. And to give me the y values, you're going to have to go back to the original equation. You're giving me points on the graph of a function. And so in that problem, you're going to find that original equation, plug those x values in, and that's going to give you the y values. And so when I plug 3/2 into that original equation that I have circled in yellow, I got -1/8. When I plug 2 in, I got 0. And so those are the inflection points on this graph, or places where the concavity changes. All right, I think I have one more topic in this video. So we learned that the second derivative tells us whether a function is concave up or concave down. But we can use the second derivative to test and see if critical numbers are maxes or mins. And this concept is called the second derivative test. So I have the second derivative test written out mostly visually on the screen. If you want to see a more formal definition, there's one in your textbook in this section. But the second derivative test basically says, if you find a critical number by setting the first derivative equal to 0, all right, so if you find a place where there is a horizontal tangent line, or a place where the first derivative equals 0, and you take that critical number c and you plug it into the second derivative, if the second derivative is positive at your horizontal tangent line, then the function is concave up, and therefore it has to be a minimum. Okay, so if the second derivative is positive at a critical number, you have to have a minimum. Whereas if you have a critical number, so again, a place where you have one of those horizontal tangent lines, and the second derivative is negative, that tells you your graph is concave down, and therefore that has to be a maximum. If you end up plugging that critical number into your second derivative and you happen to get a 0, it just means the test is inconclusive. That could be a max, could be a min, could be neither of those things. All right, so let's see how this works by actually doing an example. So use the second derivative test to find all relative or local extrema of the function f of x equals x plus 4 over x. So the first thing I'm going to do is find my derivative and set it to 0. I want to find my critical points first. So there's my first derivative. Derivative of x is 1. Derivative of 4x to the negative 1 is negative 4x to the negative 2, or minus 4 over x squared. I decided to get a common denominator to make it easier to set this equal to 0. So I basically said that this 1 is like a 1 over 1. And then my LCD was x squared, so I multiplied top and bottom by x squared. And so that's how I ended up getting that x squared minus 4 over x squared. Okay, so I got a common denominator. There's my first derivative. The only way a fraction can equal 0 is if the top equals 0. So I set the top equal to 0. I guess I didn't show all my work here, but I added 4. Took the square root, don't forget the plus or minus, x equals plus or minus 2. Now, technically when we find critical numbers, we do always have to think about, are there any places where the derivative is undefined? And if we set the denominator, this x squared equal to 0, we do get x equals 0. However, x equals 0 is not going to be a max or a min, because it's not in the domain of the original function. So if you look at this original function, we can't divide by 0. There's an x in the denominator. And so therefore, x cannot equal 0. Or I guess you could think of it as there's an asymptote at 0. So x equals 0 is not in the domain. We're not going to consider that value. There's no way it could be a max or a min if it's not even in the domain. All right, so we only have to worry about the -2 and the +2. Are those maxes or mins? And so if I'm going to use the second derivative test, what that means is I have to compute my second derivative. So rather than using the quotient rule, I've just looked at this first statement I had for my first derivative. And so the derivative of 1 is 0. And then I guess I thought of this as a -4 x to the -2. I brought the -2 down. Oh no, did I make a mistake? Oh, I think I did. Let's see if we can fix this. Right, so I've got 1 minus 4 over x squared. So I brought the -2 down. Yeah, it should be a +8. And then x to the -3, because you minus 1 from the exponent. So that should be a +8 over x to the third. Okay, so now that we have that second derivative fixed, what are we trying to do? We're trying to figure out if our critical numbers, 2 and -2, are local maxes or local mins. And so the next thing we have to do is take those numbers, plug them into our second derivative, and see what happens. And so if I take 2 and I plug that into my second derivative, so the second derivative was 8 over x to the third. If I plug 2 in, I get 1. And the important information about that is that's positive. If you have a positive second derivative, that tells you the graph is concave up. And if you have that upward curvature at your critical point, it has to be a minimum. So 2 has to be a local min. And then we're going to do the same thing with -2. So when I took -2 and I plugged that in, I got 8 divided by -8. That was -1. Again, the important thing about that number is it's negative. Negative second derivative tells me the graph is concave down. And if a function is concave down at a critical number, that has to be a maximum. So we know that we have to have a minimum at +2 and a maximum at -2. To finish, we are going to give the y values at those points. And so I took x equal 2, I plugged that into my original function. Here's my original function. When I plugged 2 in, I got 4. So I have a min at the point 2, 4. And I have a max at the point -2, -4. I don't know if any of you are bothered by those numbers. If not, that's fine. We did this right. Well, once I fixed my mistake, we did this right. I don't know if it looks weird that our min has a bigger y value than our max. Our max has a y value at -4. It's because this function does have an asymptote at 0. It's got these two separate kind of chunks to the graph. If you graph this function on Desmos, it looks something like this. And you can see that our work was correct. At +2, we have a min. All right, so at +2, we have our min here. The function is concave up. At -2, we actually have a local max, and the function is concave down. All right, that's it for this section. As always, please let me know if you have any questions. I'm happy to do more examples during office hours.